There is something strange about being human. We are very good at understanding things that are close to our own size. A room, a car, a building, a mountain, even an airplane. But the moment the scale becomes too large, something happens inside the human brain. The numbers stop meaning anything. 1,000 kilometers is difficult to imagine. 1,000,000 kilometers becomes almost meaningless. 1,000,000,000 kilometers is just a word. And 1,000,000,000 light years? At that point, the number may as well be infinite. So forget the numbers for a moment. Instead, let's do something different. Let's zoom out. Start with yourself, then your city, then your planet, then the solar system, then the stars, then the galaxy, then the galaxies beyond it. And we'll keep going until the familiar universe disappears completely. Because the deeper we go, the stranger one fact becomes. You are much smaller than you think. But so is almost everything you've ever seen. Imagine a human being standing alone. Compared with the things around us, we feel reasonably large. We can walk through forests, climb mountains, build skyscrapers, cross oceans. We can even launch machines beyond our planet. From our perspective, humanity looks powerful. But place a human beside a blue whale, and the scale changes immediately. A blue whale can reach roughly 30 meters in length and weigh well over 100 tons. Suddenly, a human looks tiny. Now put that whale beside a skyscraper. It disappears again. Place the skyscraper beside a mountain. It becomes almost insignificant. Mount Everest rises nearly 9 kilometers above sea level. That sounds enormous, and it is, until we change the scale again. Because Earth itself is about 12,742 kilometers across. Everything humans have ever built occupies a microscopic fraction of it. Every city, every road, every battlefield, every civilization, every person you've ever known. All of human history has happened on one small planetary surface. And Earth is not even close to the largest object in our immediate neighborhood.
Now leave Earth. Travel outward. The moon is about 384,000 kilometers away on average. That distance already feels enormous when you imagine crossing it. But the moon is only one small object orbiting one planet. Continue outward, and you reach the other worlds of the solar system. Mars, Jupiter, Saturn, Uranus, Neptune. And now the scale begins to change dramatically. Jupiter is so large that more than 1,000 Earths could fit inside it by volume. And yet Jupiter is still tiny compared with the Sun. The Sun contains more than 99% of the total mass of the solar system. Its diameter is roughly 1.4 million kilometers. If Earth were represented by a small marble, the Sun would be a giant sphere compared with it. But here's where our intuition fails again. The Sun feels enormous because it is enormous compared with Earth. Yet astronomically speaking, the Sun is not a particularly unusual star. It's a fairly ordinary star. And there are stars out there that make our Sun look almost insignificant. Consider a red supergiant. Some of these stars expand to hundreds of times the Sun's radius. If one replaced our Sun, its outer layers could extend far beyond the orbit of the inner planets. The planets we think of as distant worlds would suddenly be inside the atmosphere of a star. And this tells us something important. Size is relative. Earth is enormous to a human. The Sun is enormous to Earth.
A supergiant is enormous to the sun. But even the largest stars are only the beginning. Because stars don't exist alone. They exist in enormous collections. Look back at the solar system. From this distance, the sun dominates everything. But now zoom out far enough to include neighboring stars. The sun becomes one point among many. Keep going. Thousands of stars. Millions. Billions. Eventually, you see the structure they form. A galaxy. Our galaxy. The Milky Way. It is a vast rotating system more than 100,000 light years across. And somewhere inside that enormous structure, we live on one planet, orbiting one ordinary star. NASA currently describes the Milky Way as a spiral galaxy, spanning more than 100,000 light years, with our solar system located roughly halfway from its center. The Milky Way itself belongs to the local group, alongside more than 50 other galaxies. Try to picture that. Light travels about 300,000 kilometers every second. And even moving at that unimaginable speed, it would take roughly 100,000 years to cross the Milky Way from one side to the other. Human civilization has existed for only a tiny fraction of that time. Our entire recorded history is essentially a moment inside one small region of one galaxy. And we're still not done. Not even close.
Now, imagine leaving the Milky Way behind. At first, it looks enormous, but continue moving away. The galaxy becomes smaller and smaller and smaller until it becomes one glowing point. Then you notice something else. There are more points. Thousands, millions, billions. The universe is not made of one galaxy. It's filled with galaxies. And galaxies are not randomly scattered like dust. They form groups, clusters, superclusters, walls, filaments, and enormous regions of relative emptiness. Together, these structures form something much larger, the cosmic web. Start with our own neighborhood. The Milky Way belongs to the local group. Our nearest major neighbor is Andromeda, roughly 2.5 million light-years away. Two enormous galaxies, separated by a distance that is almost impossible to visualize. And even that is only our local neighborhood. Zoom out farther. The local group becomes a tiny region within a much larger cosmic environment. Galaxy groups interact, galaxies merge, clusters form, gravity pulls matter together. And over billions of years, this creates enormous structures stretching across hundreds of millions of light years. NASA describes this large-scale arrangement as a cosmic web. Galaxies, groups, clusters, superclusters, and walls connected by thread-like filaments with enormous voids between them. Think of a sponge. The dense parts are filled with matter. The holes contain much less. Now imagine that sponge is not the size of your hand, but hundreds of millions of light years across. That's closer to the architecture of the universe. And this is where something fascinating happens. The emptiness becomes part of the story. We tend to imagine space as mostly empty, with galaxies floating inside it. But on the largest scales, matter is arranged into an intricate pattern. Filaments connect dense regions. Galaxies gather around those structures, and between them are enormous cosmic voids. These voids aren't literal holes punched through space. They're vast regions where matter is much less concentrated than average. The universe, in other words, has structure. It has a kind of architecture, a cosmic skeleton. And scientists are still trying to understand exactly how that skeleton formed. The leading picture is that tiny variations in the early universe were amplified by gravity over billions of years. Regions with slightly more matter attracted more matter. Those regions became denser. Structures grew. Filaments formed. Galaxies gathered.
and the cosmic web emerged. Recent observations continue to push this story backward in time. JWST has identified galaxy arrangements showing that filamentary structures existed surprisingly early in cosmic history. NASA's Webb observations have revealed a roughly 3 million light-year-long filament containing distant galaxies and anchored by a luminous quasar.
So the cosmic web wasn't something that suddenly appeared billions of years later. Its roots go deep into the early universe. Now, keep zooming out. A galaxy cluster becomes a dot. A supercluster becomes a dot. Hundreds of millions of light years become billions. And eventually, even the largest structures we know become only pieces of something larger. This is where the numbers become almost absurd. Some proposed structures extend for billions of light years. The Hercules Corona Borealis Great Wall, for example, has been discussed as a candidate for an extraordinarily large structure, although its exact nature and significance remain debated. And that's an important distinction. When we talk about extreme cosmic structures, not every enormous feature is equally well established. Some are robust observations. Others are candidates whose true size, coherence, or even physical status is still being investigated. Science doesn't become less interesting when the answer is uncertain. Sometimes uncertainty is the interesting part. Now, imagine you're looking at the entire observable universe. Not the Milky Way, not the local group, not one cluster. Everything we can potentially observe. The observable universe is roughly 93 billion light years across. And here's the part that sounds impossible. The universe is only about 13.8 billion years old. So how can the observable universe be much larger than 13.8 billion light years across? Because the universe hasn't been sitting still. Space itself has been expanding while the light was traveling. The light from a distant galaxy may have started its journey billions of years ago, when that galaxy was much closer to us. During the journey, the space between us expanded. So the distance we associate with that galaxy today can be far greater than the simple calculation of speed of light multiplied by travel time. And this is why cosmic distance is so different from ordinary distance. When you look far away, you are not just looking across space, you are looking backward in time. Think about what that means. When you look at the moon, you're seeing it about 1.3 seconds in the past. When you look at the sun, you're seeing it about 8 minutes in the past. When you look at a distant star, you may be seeing it thousands of years ago. When you look at a galaxy millions of light years away, you're seeing a version of that galaxy from millions of years ago. And when Webb observes some of the most distant galaxies, we are seeing them from a time when the universe itself was still incredibly young. In January 2026, NASA confirmed the galaxy MOM-Z14 at a redshift of 14.44. Its light has been traveling for roughly 13.5 billion years. We see it as it existed only about 280 million years after the beginning of the universe. Think about that. The telescope isn't simply showing us a distant galaxy. It is showing us a galaxy from an era before Earth existed. Before the sun existed. Before the Milky Way had developed into the galaxy we know today. We're looking almost all the way back toward cosmic dawn. And Webb is changing our picture of that early universe. The deeper we look, the less the young universe resembles the simple picture we once imagined. But now we reach a boundary. Not a physical wall, not a giant shell surrounding everything. A boundary created by something much simpler. Light has a finite speed. There are regions of the universe whose light has not had enough time to reach us. and there may be regions whose light will never reach us. That means the observable universe is not necessarily the entire universe. It's simply the portion that is observable from our location, given the history and expansion of space-time. And this distinction is enormous. Because when we say the universe is 93 billion light-years across, what we're really describing is the approximate scale of the observable universe. We do not know the total size of the entire universe. It could be vastly larger. It could be infinite. And there is currently no confirmed physical edge where the universe simply stops. So if you were somehow able to travel farther and farther, you would not necessarily reach a wall. You might simply continue through more space. And then comes one of the strangest questions in cosmology. If we cannot see beyond the observable universe, what is out there? The honest answer is, we don't know. There are hypotheses, there are mathematical models, there are ideas involving inflation, topology, multiple cosmic regions, and even multiverse scenarios. But these should not be presented as established facts. The multiverse is not something astronomers have photographed. It is not a confirmed neighboring collection of universes waiting beyond the edge. It is a class of hypotheses that emerge in some theoretical models. And that distinction matters. Because the unknown should not be filled with imaginary certainty. The unknown is where science begins. There's another important twist. Even the part of the universe we can observe is not necessarily fully visible. A telescope doesn't automatically see everything that exists within its field. Some galaxies are too faint. Some are too distant. Some are hidden behind dust. Some emit light at wavelengths our instruments cannot detect directly. And some of the universe's most important components don't shine at all. Dark matter doesn't glow. Dark energy doesn't appear as a visible object. Yet both are central to our current understanding of cosmic evolution. So when we look at the night sky, we are not looking at the universe as it truly is. We're looking at the universe through a very narrow window. A window defined by light, instruments, physics, and time. And that window is getting better.
The James Webb Space Telescope is pushing farther into the early universe. The Euclid mission is designed to map enormous portions of the cosmic structure and study how the universe's large-scale architecture evolved over billions of years. Its mission is specifically aimed at reconstructing the geometry and evolution of large-scale structure. And future observatories will expand that map even further. We're moving from individual galaxies to populations of galaxies, to three-dimensional maps, to the structure of the cosmic web itself. The goal isn't just to count galaxies. It's to understand why matter ended up where it is, why some regions became dense, why others became empty, how dark matter shaped the architecture, how galaxies formed, how black holes grew, how the universe changed from an almost uniform early state into the enormous cosmic structure we see today. In other words, we're not just zooming out, we're reconstructing the history of the universe. And now, zoom out one final time. Forget the Earth. Forget the solar system. Forget the sun. Forget the Milky Way. Forget the local group. Forget galaxy clusters. Forget superclusters. Forget the cosmic web. Imagine all of the galaxies we can observe as points of light inside an enormous sphere. That sphere is our observable universe, approximately 93 billion light-years across. Inside it are countless galaxies, stars beyond counting, black holes, neutron stars, nebulae, planets, dark matter, dark energy, and possibly worlds that contain forms of life we have never imagined. Now, look back toward Earth. Somewhere inside that enormous sphere, there is a tiny planet.
On that planet is a thin layer of atmosphere. Inside that atmosphere are oceans and continents. On one continent is a city. Inside that city is a building. Inside that building is a room. And inside that room, a human being is listening to this story. You. And here's the strange part. From the perspective of everyday life, you are incredibly small. But from another perspective, you are part of the universe that is capable of observing itself. The atoms in your body were forged through cosmic history. Many of the elements that make up your body were created inside stars and distributed through space. The planet beneath you formed from material left over from earlier generations of stars. The light reaching your eyes may have traveled for billions of years before finally ending its journey inside your brain. So when you look into the night sky, you are not looking at something separate from yourself. You are looking at your own cosmic history.